In this video, we discuss some problems related to IUPAC nomenclature of aldehydes and ketones. Before you view this video, it would be in your best interest to view videos 338 and 339 that come immediately before this, where I walk through step by step how to go about determining the IUPAC names of both aldehydes and ketones. The focus here is to apply the information from those last two videos toward some applied problems. Let's take a look at this example problem where we are tasked with determining the IUPAC name of the following molecule. So I'm going to pose this as a question, IUPAC name, question mark, and I'm going to draw out a structure of a molecule that you should be aware of and able to determine the name of by the time we finish reviewing this video. So we're going to draw this all out here. All right, so let's take a look at this structure and determine the full IUPAC name for this particular molecule. Taking a look at this, we need to find the longest carbon chain, and that longest carbon chain is going to be driven by whichever functional group is present in this molecule that has the highest rank in the hierarchy. I notice three different functional groups of note here. The aldehyde group here at the end, carbonyl directly bonded to a hydrogen, a ketone group over here because this is a carbonyl directly bonded to a carbon and directly bonded to another carbon. And then we also have an alkene group over here. In the hierarchy for determining IUPAC names, what we found was that aldehydes rank the highest of these three groups of interest. Next up in the lineup was ketones. And third in the lineup was alkene carbon-carbon double bonds. Now I'm only focusing here in the hierarchy on the three groups that are actually present in this molecule. If you want a more complete list, take a look at the video just before this where we looked at nomenclature of ketones in video 339. So based on this hierarchy, what this tells us is that we need to start numbering from the end closest to the aldehyde, and that the aldehyde has to be a part of the longest carbon chain of this molecule. So following that, our longest carbon chain has to contain this aldehyde group, which I've highlighted in pink. Coming through to find the longest pathway through the molecule, we get to here, and we have a choice to make at this crossroads. We could come up here and get 2 more carbons, or come this way and get 3. Take the longer path. So we come through here to take the longer path. Now we number that longest carbon chain. We number according to the hierarchy, meaning that since the aldehyde is highest up in the hierarchy, we start numbering from the end closest to the aldehyde group. And that's going to put the aldehyde at carbon number 1 because the aldehyde will always be at one end of the molecule or the other. And since the aldehyde is our highest ranked group of this, that means that the aldehyde is going to be at position number 1 of our longest carbon chain here. Now, we will go about coming up with the parent name for this based on the fact that we have an aldehyde group present. We need the term Al in the parent name, such as hexanal, since we have a 6-carbon chain. However, this 6-carbon chain has an alkene group in it as well, so it's not appropriate to call this hexanal because the AN there indicates to us that there is just carbon-carbon single bonds. That's not the case. So instead, the parent name here needs to take on hexenal, indicating that there is an alkene group present within the molecule. So in order to get the name completely correct for this, since the alkene group could be at a variety of positions along this chain to create different constitutional isomers, we need to specify exactly where the alkene group is located. Remember that to specify the location of alkene groups, we indicate the numerical location where the alkene group starts. So the alkene group, based on our numbering system, starts at carbon 4. So hence, we would refer to the parent name of this molecule as hex 4-ene, designating that the alkene group starts at carbon 4 of our chain, and then Al. And we do not need to specify for hexene 1Al because it's implied that the aldehyde group has to be at position 1. An alternative way to specify this would be to call it 4-hexene al, and that 4 has to go with the alkene group. It can't possibly go with the aldehyde group because an aldehyde group by definition has to be at carbon number 1 of the chain always. That's why we don't designate that it's at position 1, because that's where it has to be. So it would be redundant to say it's at position 1. So hex 4-enal or 4-hexenal would be the parent name, and that incorporates everything that we've highlighted in pink, including that alkene group. Now our next task is to go in and identify the branches coming off of that pink parent chain. The parent chain forms the last part of the name. The branches are going to form the prefixes, or the first part of the IUPAC name for this molecule. So we have a carbonyl group at position number 2. Carbonyl groups, when they are branches, we refer to as oxo groups, OXO. So this would be 2-oxo. And at position 3, we have an isopropyl group, so we'd call this 3-isopropyl. Listing these in alphabetical order, I in iso comes before O in oxo. Therefore, we put 3-isopropyl first, so 3-isopropyl, separating numbers from letters using dashes, -2-oxo, and if we use the term hex 4-enal, then oxo and hex run completely together there. So with this, we have most of the IUPAC name in place. The last remaining component is a throwback to our unit on alkenes, where alkenes can exist as both cis and as trans configurations, or cis and trans isomers, as we could also refer to them as. Remember that the cis, if we followed the parent chain, forms a bowl, and that bowl could be the general shape of a bowl here, like an upright bowl that you would put cereal right here, or whatever your favorite thing to put in a bowl is. The bowl could also be, sadly, tipped upside down. It could be tilted to the side like this. However you want to do it, you can imagine that it is a bowl shape as we follow the parent chain. Trans is going to form a zigzag relative to the parent chain, like so, or alternatively like this, or however you want to look at it relative to the double bond. It's not going to form that bowl shape where both of the bonds coming away from the alkene group are oriented in the same direction, both down, both to the right, both up. Instead, one's going down relative to the carbon of the double bond, one's going up, one's going right, one's going left, however you want to look at it. So in order to truly come up with the complete name for this, since alkenes exist as two different stereoisomers, cis and trans, we need to designate whether this alkene group is the cis or trans designation. And here, it certainly follows the zigzag pattern. There's no sign here of this looking like a bowl. For it to be a bowl, this bond would have to be pointed upward so that it was going toward the same face of the molecule as going from 4 to 3 there. And so therefore, we refer to this instead as that zigzag pattern. So we would call this trans, and you put that stereochemistry designation at the very front end of the name. So we trans-3-isopropyl 2-oxo-hex 4-enal. Or if you wanted to use the parent name 4-hexenal, that would work as well. So that's going to be our complete IUPAC name for this particular molecule. Let's do one more example problem where rather than being given the structure and converting it into the name, here we are given the name, this long thing, and asked to convert it into the line angle formula, also known as the skeletal formula. Let's go ahead and get started with this. The strategy I recommend for tackling this problem is begin with the carbon chain. That's going to be our anchor for the entire molecule. Since the parent name here is oct6ene3-one, that implies to me that we need to create an 8-carbon chain. So I'm going to go ahead and draw in an 8-carbon chain. We need to keep in mind that on that 8-carbon chain at position 3, we need a ketone group because that's the 3-one. One refers to a ketone. And at position 6, we need an alkene group. Let's go ahead and start sketching that out. So of our 8-carbon chain, I'm going to start here. And when I get to position number 3 of the chain here, 1, 2, 3, that's where I'm going to plug in my ketone group. Since we're at the bottom part of the zigzag line here, I'm going to aim my ketone group downward to allow us to keep the zigzag line going and space out those bonds here, here, and here as far apart from one another as possible. So we've evenly spaced those, much like a 3-prop plane there. Continuing onward, There's carbon number 4, carbon number 5 down here, carbon number 6 up to here. I'm going to go ahead and number that. And then we are at our alkene group is at position 6. I pause here because we have the designation at the front end of this molecule that this is a cis configuration or cis isomer, which means that our alkene group will need to form a bowl shape. So to make the alkene group form a bowl shape, what I can do is come over to here with my alkene group. That brings us onward to carbon number 7. And then we have two options here. We can either keep zigzagging along and take the bond upward like this, or we can come down like so, like my laser pointer is doing. We want to follow what I'm doing with my laser pointer here because that will allow us to create the upside down bowl shape that enables this to be described as the cis isomer. So we come up to here and down to here. That's like a tipped over bowl because this bond and this bond coming away from the alkene are on the same face of the molecule. They're both going downward relative to the carbon of the alkene that they're bonded to. So that makes this fit the cis designation. And then position number 8 from there. So we have our 8 carbon chain, hence oct. We have our alkene group at carbon number 6. So I'm going to check that off up here. And we have at position number 3 our ketone group. So I'm going to put a check mark here to remind myself that we've got that tended to also. We have additionally accounted for the fact that this is cis, so I'm going to put a big check mark there at the beginning of the name as well. Now with that in mind, what we have left to contend with here are the branches, which I'm going to highlight here in green, and I'll sketch those out in green to color code them. Notice here that we have these listed as we should in alphabetical order. The T of tert-butyl is not included in alphabetizing because it's a hyphenated term. That's one of the nuances of nomenclature, is that if you have a hyphenated term, such as tert-butyl or sec-butyl, you alphabetize based on what comes after the dash. So the B in butyl, C in chloro, and H in hydroxy are listed in alphabetical order. Now, to plug these in, we need to put each of those branches at the appropriate location, recognizing what each branch looks like. So 4 is right here. So that's where we're going to put our tert-butyl group. So I'm going to draw a tert-butyl group. Tert-butyl group looks like a T. That's how I remember what it is. Since it has that term butyl in there, that implies there's 4 carbons in total. There's 1, 2, 3 of those methyl groups here, here, and here. And then the 4th carbon is right here. So it's this T type shape there of tert-butyl. Now at position 6 of our chain, which we've numbered, we need to put a chlorine atom in. So I'm going to put a chlorine atom right here at position 6. And at position 5, we call it 5-hydroxy. A hydroxy group is an alcohol group, and therefore we put an OH group right here to finish off the complete IUPAC name line angle formula drawn here. And as you do this, remember to keep all aspects in mind. It's a good idea to check off that you have done everything. We've checked off the parent name and the stereochemistry, that being cis. We've checked off that we've put a tert-butyl group at position 4, a chlorine atom at position 6 of our chain, and a hydroxy group or alcohol group at position 5. So this takes care of the complete name for this molecule. With this information in mind, leveraged with the content of the earlier 2 videos for naming aldehydes and ketones, you should now be comfortable with determining the names or drawing the structures for a variety of aldehyde and ketone molecules that include linear molecules with a variety of branches coming off, such as this, as well as cyclic molecules as well, where the atoms of the ketone group form a ring that has branches coming off of it.